trial and error method isn't proven to be quite as efficient as possible. So part of it is that there's other ways of looking at it, maybe more scientific, more systematic. And to discuss that with us today will be Patricio Mendez. Patricio is the Welco Industry Chair of Welding and Joining here and Director of the Canadian Centre of Welding and Joining here at the University of Alberta. Before joining the University of Alberta, he taught and researched at the Colorado School of Mines, and before that a consultant engineer at Exponent, and also was a co-founder of Semi-Solid Technologies in Cambridge, Massachusetts. So Patricio holds a PhD and MS degree in materials engineering at MIT, mechanical engineer from the University of Buenos Aires in Argentina, and many distinct awards for the IIW, AWS, and the National Science Foundation. And so, no further ado, ladies and gentlemen, Dr. Patricio Mendez.
All right, I think it's good enough. So, thank you, Bruce, for the introduction. And the first, I'd like to say, before I turn on any slide, I want to say a couple of things. First of all, I want to welcome everybody to U of A. I see lots of familiar faces, and I haven't had the chance to shake hands with everybody, but I think lots of good friends here. And I'm super happy that you're here at U of A, and I hope to see you around very often too. You can come through the lab, and you'll see it's a great experience. The other thing I want to say is, I don't know how many of you, I've been on this side of the room, and looking in that direction and seeing the pool of talent that it is in here. And I lived in Argentina, I lived in the US, I lived now in 2 cities in the US, and I've never seen a situation in which you put together a meeting and so much knowledge is put together. Actually, I cannot even go to a birthday party for my daughter without running into people that if I had to hire as consultants, I couldn't pay with a year of salary, right? So, the pressure is on, but this is the good news. I'm sure somebody will catch me on something that could be said or done better, but I'm sure there will be also somebody that with whom things will fly by, depending on the topic. But so thank you very much for being here. Well, how about this? Huh? I want to talk a little bit about procedure. And here's a funny thing: when you say procedures here in the province, everybody has a different take, right? For the most part, I hear people associating procedure to codes, or to quality, or to pass-fail, or to lots of different things. And my whole presentation is essentially this slide. I believe that when we design a procedure, there's an optimal point. I haven't been in the field as much as many of you, but thanks to many of you, I learned, and some of you are here. Who taught me much. And what I heard is that if you give like 2 or 3 companies to develop the same procedure, to make the same weld, they'll come up with 3 different procedures. All of them pass. Now, I do believe, and I'm going to make my point, that there is an optimum. But I believe we're shooting all over the place. And that's the whole point of my talk, is if there is an optimum, does it make sense to shoot all over the place blind? Well, maybe. We'll discuss this. So I didn't come up with this by myself alone. Now, the funny thing is that my other 2 co-authors didn't show up tonight, and I don't know what to make of it. And I got big apologies and blah, blah, blah from them. But for talking, that's my job. And so they're supposed to be the real ones fielding the tough questions. So we'll see how it goes. I'm going to make it so long so there are no, I'm not going to. So one is Stuart, who's another student in the lab. He started convinced that he wanted a master's, and now he's convinced he'll do a PhD. and I think it's a good choice. He loves our lab too much. And the other is Jim Gilbeck, who I believe doesn't need an introduction. So here's my credibility. Here's me. I'm the Welco industry chair in welding and joining here at the university. And on this slide, I would like to make a special acknowledgement to Doug Schindel here, the president of the Welco companies, because he's being the welding evangelist behind getting not only his own company, but a few other big fish to commit to having this program at the University of Alberta. And I'll show you a couple things to have a sense. So now that I talked about how we have a target in which there is an optimum, and we're shooting all over the place, I'm going to show you that I know somewhat of what I'm talking about. That's me. That's me.
Like the shorts.
And I was going to say, you have to believe anybody wearing those shorts, huh? But in the 80s, come on, who was alive in the 80s? Anyway, so that's me. I used to shoot archery, and in this previous slide, I would be the ones shooting the whites there, so you decided to take engineering better. So, it's a beautiful sport. So, I believe most of you know me, and those of you who know me know that I like to talk about myself. Those of you who don't know me, then I'm going to say this to you. So, the charming accent is from Argentina, as Bruce already scooped me, right? And there's Argentina, right? If Canada is the northernmost country in the Americas, well, Argentina is the southernmost country in the Americas. Well, depends on the Chileans, but that's another conversation. So there I got my mechanical engineering degree, and I'm a design engineer. And when I was there, I worked in the Office of Naval Research, which is nothing like the American Office of Naval Research, and I was a pioneer doing research on wind turbines. And now I saw the light. I do oil and gas. It's I worked at the beginning of straying into the dark path, right? Was at Tenaris, that is an integrated steel maker that makes pipes for the oil industry. And actually, Tenaris has a plant in Nisku. It's one of the few good things left in Argentina. It's an Argentinian company that became multinational. So from Buenos Aires, I flew to Boston. It was the dream of my life to study abroad. I was very fortunate of getting into MIT. That was a very good university in many aspects beyond rankings. And I did my master's in material science in something called semi-solid metal processing. I'm not going to get deep into that, but I could talk lots about that. It's a very interesting thing. Actually, even got a patent for welding in this state. One day we might use it. I got my PhD on welding at high currents, and here I touched the welding machine. Actually, I used to weld a little bit in Argentina, not as a real welder, but as my experiments in the Office of Naval Research. We had to put together a contraption with zero budget, so I was scouting for the electrode tails to weld my thing. That's life is very different now. In Boston, I also started up a company using this semi-solid metal processing, and we invented a machine that we licensed to Ford, and Ford used it for many years around the turn of the millennium to make parts. I thought I was going to be independently wealthy. I made a little bit of money, and then I needed to get an honest job. So here you see me. I was a consultant. Talking about honest job, I was a consultant in litigation for a while, but that was good, especially good money. But it's not my calling. From Boston, I went to Denver, where I was a professor at Colorado School of Mines, and I taught many things related to metallurgy and welding. I taught a class of welding that was awesome, about the physics of welding. It was the last year when nobody could hold it against me, just before coming here, and I went super deep. And I was part of the Center for Welding, Joint and Coatings Research. See this photo? This is on top of Mount Evans. That is the highest paved road in North America. So I'm pretty proud of that. So there it goes. I missed that aspect of Colorado. But from Colorado, me and the family moved here to Edmonton, where we found something actually a lot more interesting than just riding my bicycle. And that was to put together the Canadian Center for Welding and Joining, for which, again, Doug and all the other companies that participated in this, I'm much grateful. So let me tell you a bit about this center, because many of you are familiar with that there was a welding program at U of A that was led by Professor Patchett, and actually I believe we have at least 2 people who work with him. We have Matt. Can I see a show of hands who work with Barry Patchett? Okay. All right. So I see like 4 or 5. But my hope is at one point in life I can ask this for the same show of hands, and we'll be, yeah, Patricio, yeah. So, no, like everything in life, Barry had to retire, and for a while there was no coordinating welding research. And actually, I think, and I cannot say this outside these walls, but I don't think the university missed it all too much. You guys in industry did. And eventually came back to the university, and our dean, who's not slow at all, said, of course we can bring the welding program back, but it's going to cost you. Is that right, Doug? But it ended up happening. So the Weld Co-Industry Chair was created in 2007. Here you have the 2 happy pioneers smiling, and I was hired in 2009. And these 2 years is what it takes to hire quality people. And I want to meet you. So look, this thing is no minor feature because it's a $3.5 million endowment. And typically, if you go to places like Harvard or even MIT, they also have endowments, often bigger than this. Typically, it's a very rich old guy dying, saying, I give you all the money. Well, thank God, all the people involved here are alive and need to work to earn their money. So this means this endowment that was put in here for us is not out of charity or like nostalgia, but out of what they see for the future of which they are part. This is a big deal. This is a big deal. I don't know of any other endowment done at this level by active people. Our lab opened on May 5th, 2010. That is not too far after. And by now it's a $3 million facility. And I hope many of you have seen it. And if not, we'll have a chance, I don't think tonight, but at some point, come visit it. We are up to par with pretty much anybody else in the world. And we're working on still going farther. We created, together with the people from AITF and the people in the government, the provincial government, and the AMFI that Bruce already mentioned, that is one of our outreach operations. And we opened actually a new facility in 2011. So right now we have 3 labs. We call it 1 lab, but it's in reality 3. We have an industrial advisory board made by the companies who participated in the endowment. We have a long list, and I believe many of you are going to see yourselves in this list of people who have contributed with research, consumables, training, equipment. Everybody here in the province and in the city did everything they could, and I got more attention and goodwill from American companies now that I'm in Canada than when I was in the US. Go figure, but it's true. So here is a recent picture from our lab. The photo doesn't involve everybody, but here we can point some of the students. I see we have Gentry, we have Nairn. I just kept Nolan. Nolan started to work on welding for civil structures, but went to fully civil. But he still, we love him very much. We have Steve. We have Atta. And I'm forgetting any other student in the lab. All right. So that's great. And we have, this is reading week, so all the undergrad students are enjoying the good life. But we have right now 9 undergraduate students working in the lab too. So Something that I think is especially good of our lab is the equipment we have. And the reason we have this good equipment is with the generosity of Mailer and Lincoln, we got the free welding machines, and we could use any other budget to buy equipment that is very sophisticated. We have hardness testers, we have hydrogen testers, we have instrumented Sharpie. Look at this. This video you see here is among the best you can get in the world right now for seeing welding as it happens. Right? It's, in this case, you got to see globular, now spray transfer. You see now short circuit transfer. And the cameras to do this are very expensive, right? And they don't give me the demos for free. Right? This is a $40,000 camera. And as we accumulate experience and this type of equipment, we're becoming very unique. Look, this super new. This is tungsten carbide powder falling from a 2-meter wire and in a nickel weld pool, right? When on our session on May 16th, that we're going to have a day-long seminar on on overlays for wear protection. I'm going to be talking a lot more about this and other of the work we do at the lab. This is cutting edge. So, overall at CCWJ, our center, as it relates to procedure, what we work on is on the foundations about the materials, the processes, the science. We are not experts in the code, and it pains me every time I talk to the experts because I feel like I'm not too smart. We are not expert welders, but what we add, and I believe is very essential, is the putting it all together at a deep enough level where we can see what is not intuitively obvious. So, now the talk starts. How much I hate talking about myself and the lab. Well, we're pretty proud of the lab, so that's okay. So, this is my talk now. This is what I heard from my friends, and my two absent co-authors endorse it, and they are the ones who know even more. So, here in Alberta, but I believe this is way wider, because when I talk with companies in other places in the world and at meetings, I think they go the same way. A typical procedure approach is based on this: making a reasonable, good-looking weld which passes code. If you do that, bingo, that's a procedure that is made. So how do you go about that? Well, you have a welder who makes beautiful welds because you're going to present it for testing, so that he makes the best, or she makes the best possible welds. Engineers or metallurgists have nothing to do at that stage. You say, like, Joe, go weld me this pipe and do it right, and I know, and then you see if it passes. The welder and the quality department don't have a very fluid communication, and I believe, from what I heard, sometimes it's even less than not very fluid. This is the accepted practice. I believe this is, I believe 100% of our procedures in the province have been made this way. And it's economically appealing because you didn't need to do anything, you didn't need to read, you didn't need to study, you didn't need to hire anybody else. You just got this procedure made right in by the company that makes procedures, but within this group of people. And it's an approach that happens naturally. Now, if we never welded this material before, then we call friends. Here, these are examples from Jim, right? Damien Kotecki, that is this expert on stainless steel welds, and actually he was here 1 or 2 years ago talking about stainless steel. He says, okay, if you want to weld 310 that has this very sluggish weld pool, you make the ugly cold stringer beads. So it's like this magic recipe. For this material, you do this, right? Okay. Other things, other drawbacks here are things like the interpass temperature are not intuitive. So they don't add to the look, but they detract from productivity. Do you need it? Don't you need it? How do you go about it? I know Julian has a take on this, right? Now, occasionally, yeah, we say we should use this heat input. And we kind of care about the heat input. But why, and what does it mean? Go figure. But sometimes we try to stick to it. So we do this, and then we go do our mechanicals and see if it passes. So we do tensols, we can do Sharpie, we can do hardness, maybe we can do some other test if it is required. We go and see if it passes. Maybe it passes, maybe it doesn't. We don't know exactly where it would be. Now it sometimes passes and everybody's happy, and sometimes it fails. And here is something that amazed me, because before I got to be in touch with the real people like you guys, I thought an engineer made procedures. Look, it's laughable, right? So, so you have the welder deciding the current, the voltage, the velocity, and then it should pass. But if it doesn't pass, oh, okay, it didn't pass the code. So you get into these code experts, and I have a few of these who are my friends, and it's a little bit like the interpretation of the Quran, right? Well, in line so and so, you should do this or that. But then they would ask you the questions with a twist, right? And so you see if the borderline case would pass. And here we have another example from my knowledgeable friends, right? So Nay's code says you have to measure 28 points, all below 248 Vickers. Imagine one doesn't pass. So what do you do? Do you go back to scratch and start everything again? Well, how about if you repolish and test again? I mean, there's something wrong about it, right? But if it passes, we're all happy. But because it's the same weld that didn't pass before, right? Or you can ask questions. Who likes me here? So, can we test another section, or we need to re-weld? But again, this is playing a game. It's the same weld. If it didn't pass and now it passes, there is something. Imagine now it passes. Do you really think that one day the welder comes with one drink too many, or like one wife too less, or one girl too many? Something. I'm pretty sure it's pretty easy to fall out. But it might still pass. It might still pass. But then it can really fail. Then you might be in real trouble. So then you start like going like a monkey in an experiment, pressing the lever and trying to make more welds, trying all variables. And welding, if anything, has a ton of variables. And those are the ones you believe you can play with. But there are many other ones that are there too. So this trial and error often is done blindly. It does not come for free, doesn't even come cheap, doesn't happen immediately, and typically people are not happy during that time. You can involve consultants, and I have been one, and it's very good for the consultant. And by the way, I offer my services. But what I'm trying to do is that by the time you reach a consultant, you make them really work for their money. So you can even do finite element thermal models. I heard of people doing that. But you know what? I think we shouldn't be reaching this point with a little bit of knowledge. So if we close our eyes and we believe we are a weld, I don't know how a weld feels, but I'm going to imagine that, right? So if I'm a weld, there is a combination of parameters, which I'm going to call the process envelope, and I here represented it as a circle. In reality, you have so many variables that would be like a hyper geometry, right, in many dimensions. But let's say it's 2 to make our lives easy. So inside the process envelope, whatever that is, you're going to get, if we think of the NACE code, we want it to be below 248, so we can get 200, 247, some numbers that, 200, right, but numbers that go inside, we're happy. Then there are some other combination of parameters that give the things outside. So those parameters are the ones that are going to define this line. See, if the parameters that give me the good ones, a combination of parameters will give me good ones or bad ones, and the line between what combination of parameters it is defines this green line. So now, here's my point. If we qualify our procedure at this point there, and I'm going back to my analogy of the archery target, right? Of which I put my awesome shorts and I know a lot. So, if we qualify the procedure here, pass or fail passes just like anything else. But I think we have little wiggle room, right? Maybe we can move it out here, but you don't know if the bad day is going to move you a little bit that way. Now, obviously, if we could aim for the center, we would have lots of wiggle room. Right? So that's my point. And before I tell you how I believe we can aim for the center and tell you some practical examples, I want to tell you that I'm not completely naive. In real welding, like the one you guys do, in the lab everything always is very controlled, but you have lots of factors involved. You have economics, you might not have time, you might not have the money, you might not have the test materials. Sometimes they are very expensive and difficult to get. You might not even have the welders to start playing around. We have human variability, we have issues of communications. You say something so clearly, but the other person understands exactly the opposite so clearly. I know this from my trying to speak my Spanglish, but variability is in the equipment. Two welding machines are actually not exactly the same. You can ask, for example, Dale Malcolm has an awesome example about sub-arc machines, in which a bank of two welded with the same current, and a third one was different for reasons never explained, right? And also in welding, there are many things that either we don't know, or we don't want to measure, or we measure but our measurement is not good anyway, right? So let's acknowledge that that doing something rigorous or scientific about welding is difficult. I want to acknowledge that in front of everybody. But now my question is, given that it is impossible to have perfect control of what happens, does it make sense to give up control completely, just to turn it over to a welder to do a weld? And no engineer involved, no metallurgist involved, just see if it passes? I want to bring up the question, and maybe we can have a little bit of back and forth. So what I want to propose, and my two absent colleagues too, is that at least somebody should know a little bit about the causes and effect. And that's one of the reasons that justifies our existence as a welding lab here at the university and in the province. Because this requires a bit of training, and hopefully these guys sitting on this table will be on top of this. Well, they're already on top of this, but they'll prove it in practice. So the approach I suggest, if we wrap it in three general bullets, would be: let's understand the material, let's understand our temperature evolution, and let's understand the process. So material aspects. I'm going to get a little bit deeper here, but I'm talking a lot, but I'm not going to go too deep at this stage. These slides are actually from the Amphi program, so you guys might have seen them already. So here's an iron carbon phase diagram, and of course, steel in practice has much more than just carbon, right? But this steel or any other material you have, it's going to have, if you look at it in the microscope, it's going to have what we call a microstructure, with things like primary ferrite on the austenite grain boundaries, or this bainitic structure we call FSA or FSNA, intergranular acicular ferrite, so many things, right? All of these lives in a steel of exactly the same composition. The same steel, depending how you weld it, it's going to have this or that. Now let me tell you, it doesn't take a PhD to tell that toughness or strength in these two is going to be very different. By the way, this is going to be way tougher than that, but So how you do this, right? The way we can summarize some understanding about the materials, right, is through these things called the CCT curves that are tabulated in many cases, and in other cases we can use carbon equivalent to make sense out of them. So in a CCT curve, it's universal for all welding processes on the same material that depends on alloying, right? And most engineers here in the room are probably familiar with this one, but we not always use it for welding, and there are good reasons for that. I'm going to get to that in a second. Now, for different cooling rates, this graph is made for different cooling rates. So different TA5s, as if we had different heat inputs or different preheats, right? These curves are awesome. They give us hardness for a given cooling rate. They give us hardness. They give us what microstructure we're going to have, like if it is 76% primary ferrite, 16% perlite, 6% bainite. These curves tell us this. Small changes, and these curves are not absolutely universal, because if I have different heating rate to get to this hot temperature, if I have different starting microstructure, they might vary a bit. Some people might argue that it's a little bit more than a bit. But again, when we compare with absolute ignorance, with not knowing anything, right, saying, Joe, weld this, these curves talk to us. They can help us make sense of many things. By the way, in our lab, we have a machine to make these curves. And it's not a machine that comes cheap. It's 140K. That's what Atta is using for his PhD. And we hope to put this machine to good use in understanding materials to develop welding procedures. So it's not going to be ready for tomorrow, but we'll be able to say lots of things at some point here. Now, for example, what can we get out of these curves? That if we cool very fast, and this would be a curve that corresponds to fast cooling. And by the way, I haven't explained these curves in much detail. Let's look at them as a map, maybe like in a holistic sense. Of course, every line is there for a reason, and every line means something. But my point is that these curves that are tabulated are available in many cases, or we can interpret them in some other cases, right? And they tell us things. They tell us hardness, they tell us microstructure, and they tell us, for example, if we cool fast, right? If we cool at, this is, what is it, the cooling rate here? I didn't put the cooling rate. Okay, well, anyway, that if we cool down at this cooling rate, we're going to end up with lots of martensite, right? A fine microstructure is going to be very hard. See the hardness here? 32 Rockwell C. That passes any code? No, right? So, well, maybe for wear protection. Problems with hydrogen if we have that much martensite. On the other hand, we can cool slow. We'll end up with a soft microstructure, coarse, very, we look at the microscope and it's big. No martensite, that's good. Now, in the case of stainless, this is for carbon steels. In the case of stainless, we have all these sensitization, right? The chrome carbides precipitate. A good thing for carbon steels, hydrogen can leave, so it wouldn't cause a problem. We temper the previous bead. So there's kind of a balance. And just knowing this, even if I don't have the exact curve, brings something into my mind about trade-offs when I'm designing the procedure. That the guy who's welding and has a really good hand, is like a virtuoso of welding, might not know this. And this plays a role. So all these curves, these curves are typically made for steels that are heat treatable. Heat treatable steels are the steels you don't want to weld, right? Like 4340, right? So, for the funny thing is that for welding we seldom have the CCT curves, right? But we have something similar that is the carbon equivalent, right? With the carbon equivalent, we can say if I were to have a composition, a given composition, I would get a given carbon equivalent, and there are formulas that say if you have a given carbon equivalent and you have a given cooling rate or a TA5, however you want to measure it, you would end up having a given hardness, right? Now, it is true that alloy affects carbon equivalent. It is true that carbon equivalent affects hardness. Now these curves, these experimental points have so much scatter, right? It looks so precise when you talk about carbon equivalent and you get a 3-digit number. But there's a lot of scatter. But however, there is value in this. And many of you are aware of carbon equivalent and account for that when doing a procedure. Right here, I have this curve from a named company that makes pipeline steel in Saskatchewan. So it's and here they measure hardness for different cooling rates. So you get to know that that the faster the cooling rate, the hardness increases. So you could say, if I wanted this hardness, right? For example, you want the maximum strength, but you don't want to get into corrosion problems, right? Okay, you might want to aim for the 248. So it would give you, okay, we should have this cooling rate that is between 10 and 20. It would be like 13 degrees per second. Right? You can say those type of things. Now, there are limitations to this. For example, these two formulas that I got from the CWB Module 21, where is the boron? If any of you had to play with boron steels, you know that those guys get hard in the brush, right? So all these things need work, especially when we say here in this province we work with not an infinite variety of materials, but some variety that nobody considers seriously and with a good focus. So things like this carbon equivalent, I believe, needs to be revisited for what we care here in the province. Formulas like this Vickers formula, you know, these things, actually, they're in CWB Module 21, but they are lifted from another book that lifted it from another book, and welding, for the most part, always comes back to the 50s. Somebody in the 50s, in which they didn't have proper thermocouples or anything, was measuring it. So does it make sense to use knowledge of the 50s with the materials and machines of today? This is not too far off, but I think there is a little bit more improvement. So I said in our approach, we have, let's look at materials issues, let's look at temperature issues, and let's look at process issues. So I just mentioned materials very briefly, but if you come to the amphi sessions I have the dates here at the end. We'll spend a lot more time on it. Temperature aspects. So here's the funny thing of welding, right? Here you have temperature profiles. The high one is right under the arc. And after the arc passed, the temperature dissipates around. And, right? And there are, you can calculate all this. And here is, if you're right under the arc, you get this big spike in temperature, and then cools down slowly. And here is where you have your cooling rate and the T85. This is what we measure with thermocouples. And actually, in the lab, and you can ask Steve, sometimes we try to put the thermocouple inside the weld pool to measure it from the hottest possible down, and measure the cooling rate. If all goes right, one of the toys we don't have yet, but I'm working on, we should get a thermal camera and where you get to see temperatures on the plate and the gradients and the evolution with time. So let's see. Now, because I was talking too much, I felt I had to put a couple formulas to get your attention back on me, or your credibility. So there was this guy in actually at MIT, my university, in 1946, that happens to be way before me, named Rosenthal. And he came up with a formula for calculating these curves here, right? And he had to make lots of hypotheses. He assumed that all the properties of the material don't change with temperature. Well, that's a huge lie, but it's better than saying nothing. He assumed that your torch is smaller than a pinhead. Well, go tell that to the welder, right? He assumed that your plate is infinite. And I know for a fact that it's not. And actually, Q-Mars, you worked on that, right? And Russ, right? So, but he can say something that makes sense. So it's not, this is not the complete truth. But before this guy, we knew nothing about it. If you think all through World War II, people were welding battleships, cruisers, tanks, bridges, you name it. And they had no clue what they were doing. They were like, Joe was trying the welds until they passed. So this guy came up with these formulas that I present to you in all their magnificent elegance. And this is a Bessel function of second order, and the second type and order is 0. But it's in Excel, by the way. Huh? So if we grab these formulas and we take them seriously, we can come up with other formulas. And these ones fit in a single cell of Excel. And with these formulas, we can calculate T85. Or we can calculate the cooling rate in degrees per second. Yeah?
How thick do you think is zinc plate?
Oh, excellent question. Okay, this has been very studied. But the criterion is this. If you do the isotherms, let me show you. You see these curves of isotherms? If you care about an isotherm that is longer than the thickness of your plate, if you care about an isotherm that is wider than the thickness of your plate, then you're working with a thin plate. If you care for an isotherm that is smaller than the thickness of your plate, then it is a thick plate. The bottom line, you almost always, if you do T85, you almost always end up using thin plate, even if you're welding half an inch plate, right, for the most part. But this is, I can give you some clear criteria. People have worked on this. So, so you have this thick and thin, but my point here, right, and this actually have a special love for this topic, is these formulas fit in a single cell in Excel, and all these other numbers are tabulated. K is tabulated, is the heat, thermal conductivity. Alpha is thermal diffusivity. They are tabulated in any heat transfer book. Actually, they're here on the screen. So with these formulas and this table here, you can calculate cooling rates, you can calculate T85, right? HI is heat input. The heat input you talk all the time. That's what it is. So now, you should not think that because I put Greek letters here, you're going to get like 4 digits of accuracy, right? But you get the ballpark. But what matters is before you do any weld, you have a ballpark. You can say things, right? And again, I go back to my question is not how good this is. I don't know how good this is. The question is complete ignorance better than this? Is knowing nothing better than this? So I feel comfortable. I know, no, completely, this is not worse than knowing nothing. These formulas, right? I'm using the thin plate, which is what typically applies. And let's play with it a little bit. So this formula tells us that if I increase heat input by 10%, the T85 will increase by 20%. There are some other factors that we neglected here, so it's not exactly, but ballpark. That's okay. And that's an interesting thing, right? 10%, 20%. If I increase the plate thickness by 10%, T85 decreases by 20%. Right? But we know, like welders know this, the practical people know this. Right? And it's beautiful when it comes together in a quantitative way. The effect of preheat. If I increase from room temperature, to, say 25C to 75C, T85 increases by 30%. Right? And you know what? These numbers are, some people, I know some people use these for procedure development, but it's typically in the nuclear industry or in the military industry in the US, right? Or in the national labs where like time or money doesn't mean anything to them, right? But, so what I'm trying to do is if I can synthesize this, and I'm not quite there yet, but synthesize it so everybody can use it in a proper way. Effects of joint type. Look, we know it's not a factor in here, but it's part of this same analysis, and we teach it in our welding class, that a fillet weld will cool 1.5 times faster, 50% faster. We know that a butt weld. A narrow gap will cool twice as fast. And that's one of the problems with the people doing narrow gap. One of our former students is in the nuclear industry in France, doing narrow gap real deep. His welds cool down very fast. But he knows this, he's on top of it. So now roots have a fast cooling rate too. And that depends on the angle of the groove. And we can anticipate those type of things, right? There are many, many other aspects, practical aspects. But we can say some things. Effect of the materials, things you also know. Aluminum will cool faster than carbon steel, about 3 times faster. And stainless, about half as fast. We know this type of thing, but if we can anticipate it through this, we can be ready. And very often, the guy who does the weld is used to some motion in the hands, so when you change the material, not necessarily the welder that is welding for passing the procedure will immediately change what he or she are doing. So, process aspects. So I said 3 general bullets. One is materials. I talked about the CCT curves and carbon equivalent. The other is temperature. And I put my credibility with my Greek letters on the Rosenthal formulas. And the third is process aspects, right? For example, if we must fill a groove, like you guys at Welco sometimes do a single pass, right? And it has to be the right size. So mass conservation, the mass that goes in your fillets has to be the mass that comes in through the wire, right? And you account for the electron efficiency and stuff. Mass conservation. Now, you must select current and voltage. And there are lots of things that are beyond intuition, that if you know a little bit, they play a role. For example, well, we know that increasing arc length with the same current will increase heat input. We know that. Now we know, or many people will be familiar that STT or RMD or short circuit will reduce the heat input. But then there are some things that some people will say, oh, obvious, and some other people will say, I never thought of that. That increasing the contacted to workpiece distance in mechanized welding, if you keep the same voltage, is going to reduce your heat input, right? And we saw that in practice in one of our research projects. And we teach these things in class, but for people who are welding for a living, that didn't come as obvious. So these type of things, I'm hoping to bring to the table and to consider in this approach. So there are issues about energy conservation too, about melting efficiency. If you want to have some amount of dilution, right? You can have the same amount of dilution putting more or less heat. Depends on how fast your weld moves. If you move slow, heat goes through your whole plate. If you weld fast, for the same heat input, if you weld fast, most of the heat is concentrated in the weld pool. These things come from these equations, right? And some of you might be familiar with it. This applies more to mechanized welding, of course. But these type of things, that are not too many, if we put them together, I think we'll make smarter procedures. So, I'm going to go through these 3 bullets with a case study. So, let's think we want to have an X80 pipe for sour service, 248 Vickers, right, maximum. And this would be 3/8 thickness pipe welded with MIG, and this would be the steel formulation. So we have this CCT diagram from the same undisclosed company in Saskatchewan, right? And so we have the time, right? They made this one for a steel that is weldable. That is very uncommon. That is something we have the capability of doing here in the lab. And they get to see at different cooling rates how much martensite or bainite or ferrite they are going to get. And they know the hardness, right? And if you want to be below 248 Vickers, you get to see here in this line that you should be cooling at a, you should have a heat input that gives you 10 degrees per second or slower. All right, so now you don't want to go much slower because you're going to have a coarse microstructure, and that's not good. So let's aim for 10 degrees per second. And so we would go to our formula here, and for T85 typically is thin plate. I'm skipping the confirmation. And we have a formula, and it says, for the tabulated values that I put in the previous slide, these are the same tabulated values, you should have a heat input of 1.28 kilojoules per millimeter. By the way, that makes sense. That's what we often use here in the province. It's more or less 1, right? And so this is the temperature aspect. And look at this. The beauty is that without having done any weld, I already can ballpark what heat input I should do for this steel in particular to be in the good place. And then there are the process aspects. If you can, right now, look, this is pretty, I don't know if it's sad or it's funny, but the state of the art, if you have a heat input and you want to get voltage and current, of course, you can go to your experienced welder. But other than that, is this minimum? Whoa, all right. This melodramatic calculators, and that's for bad-mouthing my sponsors. So, or the welding preheat calculator. And of course, when you want to show one to the other, you say, that's cardboard, right? Yeah, but both have it, right? And now they are trying to get iPhone applications, but they're still far, far behind. I believe, because I talked to their software developers, I believe liability is an issue, that if they were to make an iPhone app for making a procedure and then something blows and kills 10 people, they would feel very, that would be a problem. I don't know how they would feel, but it's going to be bad, right? But I think it's unstoppable. This will eventually happen, that these material properties, together with the temperature, together with the procedure, with the process, they're going to be combined in some sort of software. We want to work on that. And actually, there is some work that has already been done, like Matt and my predecessor, Barry Patchett, right? Worked on an Excel formulation of putting these type of things together. So I would hope at some point to have something that everybody can benefit from, and that we have tested with our machines, and we have checked. We are not there yet. So in conclusion, there is an alternative. I believe I want to push my point that yes, there is an alternative to 100%. Let's see how it goes. That's the whole point of this conversation. This requires some basic engineering and technical skills. I believe if we do it right, will be much faster and less expensive than consultants or numerical modeling, or like doing lots of experiments, and needs to be calibrated and tested and explained and taught. It's not true that I can give you some magic software that is going to solve all the problems. No, that doesn't happen. So what are we doing here? For that, we're training some people. Here you see one of the photo of our open labs, photo from another open lab, people that come to the lab. I know I talk much, but we get serious every once in a while, and we write these heavy papers about how to synthesize all this information. If you think this looks serious, look at this. I presented this last year, but don't laugh too much. It got us an award from for the best paper on weld modeling that is given every 3 years, a single award. So it's not too bad. I want to invite everybody who would be interested in learning some more about this to come to our Amphi sessions. Will be on March 19th and 27th. We'll talk more about all this. And I'd like to stop here and have in front of you the list of people to whom we owe very, very much. Thank you.
questions. Anybody have any questions you'd like to ask Patricio?
Oh, come on, I have to have offended somebody here.
Do you think that sometimes with creating these procedures and trying to do these things that we sometimes constrain the welders a little bit too much?
Oh, excellent question, which I know from hearing, all right? But this is my understanding. When you come up with all this beautiful thing, it might be either too fast or too slow for the welder, or it requires typically too little weaving or doing these stringers. My understanding is that sometimes by luck you end up exactly where the welder wanted to be and everybody is happy. Sometimes you don't. For example, in the case of stainless. And so the problem is much bigger, right? Like from human relations to economics. Maybe you pass the procedure and you're happy and you want to go on. Maybe you don't pass. So if you don't pass, I think a good conversation with the welder might be in place. I don't know. You told me, what's your experience?
Well, it depends, right? Because you get some of these procedures where you get the welders can get a lot of free reign, and then you see some of these, like the Duplex stainless steels and other bits and pieces, where you have to be very controlled, very precise, and
right.
Every welder's going to weld that Duplex differently. So you can run into problems where one guy can weld it really, really cold, whereas the other guy can't. So sometimes, depending on even who you pick to do your procedure, can limit you because he can do it this way, but another guy can't.
Yeah. I when it comes to stainless, and especially Duplex that we're using a lot in the province, I mean, Duplex is the worst of all things because a little bit one way or a little bit the other way, it shows. Carbon steel is super forgiving. Duplex is, you're aiming for some, in Duplex there is actually a target with a center. So I don't know. I'll tell you what, I think many times the people talking to the welders do not understand things themselves enough as to say, no, believe me, there is a reason for this. Because if you can say with that emphasis, the welder, I believe, when I talk to welders, they are interested in paying attention, but if they believe you. So I think, again, it comes back to us, the ones who don't weld for real, but in the business anyway, to try to make this as understandable and as broad to everybody. That's part of this amphi thing, right? As a professor, I do my equations, but what good are those if in the end the welder doesn't use them?
Being Joe the welder, I found that welding on a little wee piece of steel this big, trying to do a welding procedure, has no relevance to what I would do in a large tank or a large pipe or anything else. Because the numbers that I'll get if I weld on a piece of steel this big and this big are dramatically different.
All right. Excellent point. So what you say, actually, the way I see it is, in the 3 bullets I said, let's understand the material. You might say the material is the same in both.
Yes.
Let's understand the temperature,
Yeah.
right? And that's where it would be. Actually, this Rosenthal equation I showed you, well, actually, there is a way of accounting for welding on pipes of different diameters. I didn't include it here.
When I hand the numbers in, the numbers have to be in a certain area. Whether I weld, it doesn't matter what size of piece I weld.
But of course, right?
They want
So
the numbers to be in a certain area.
yeah.
Procedures, or the client will only accept numbers in a certain area.
Well, so here's a little bit of an education for myself. I imagine that when you do procedures, you would restrict them to, when you do a procedure, you say if it is for a pipe of a given diameter, there is a limit to how small or how big you can go, I would imagine.
Depends on your code. It really depends on your code.
Okay, so this goes back to the passes the code or it doesn't pass the code. I believe, depending on the code, is very relevant because otherwise you cannot do your weld. But sometimes you can do things beyond what the code says because you know it's good, as long as you don't. I believe, and I don't want to be like crazy idealistic, but I think that thinking one step ahead, it might pay off in money. In cases, you say depends on the code, but you say, yeah, it's not the same, and you can account for that. And if we happen to put...
You and I could account for that, but the client still wants a certain set of numbers. And as somebody said here, the client has to be educated, yes. But when's that going to happen?
Right on, right this second.
There's a reason code allows for essential variables to have ranges.
Well,
And voltage and amperage are not essential variables because they do not affect metallurgy unless combined to come to heat input. That's why heat input is restricted. Welding ranges on a welding procedure, your amperage and voltage can vary drastically. It is, in most cases, it's non-essential variable except for CSAs and 662. But
Right.
heat input is. So essentially, code has applied what you have presented here to establish what those essential variables are.
well, right, when code talks about and it lists these essential variables, right? But there are some things, for example, we have a project on, sometimes it matters, sometimes it doesn't, but if you change voltage and current with the same heat input, you get different dilution. And right, if you have more current, you have more dilution. Right, it might or might not matter, but I think it's worth thinking. And I think in some cases, does. It's, some of the projects we have does. Yeah. And, or maybe it doesn't, right? But it's good to do it in the knowing.
So we can take it offline, but
No, that's good. Like,
with dilution, are you not trying to match your weld metal to your base metal?
we have projects in which that is a problem, right? Sometimes you use a weld metal that is different than the base metal, right? And it's more expensive, right? And often the weld metal is not exactly the same as the base metal, right? It has a little bit of titanium and a little bit of things. So it might or might not matter, right? And I'm not saying that all the time we should be doing engineering, but I'm saying never, right? Right? I don't know.
if never is a proper statement.
Right,
There's a lot of people that do.
Right. So, but for example, for duplex, would you say that you have this wide range too? No, right? Like,
But again, you're looking at different things.
Right,
a
right,
lot
right.
more engineering goes into duplex because you're looking for a ferrite balance.
right. But we'll talk some more. But so I have a skeptic here. Any other one? Like, I know I need to learn here.
Tom.
Patricio, I'm going back to Joe the welder's question for a second. What he said really points out, I'm going to talk about the 4759 code, because all the codes that you said are different. So I'm going to talk about the 47, where the inputs and all, and with the heat inputs and the electrode and everything is variable. There's initial variables and you have to follow them. But when I'm doing a procedure and I have to do a plate 300 by 150, but in the real world, I'm doing a weld that's 20 feet long. And when I weld this, by the time I get here, it's going to be different. But the procedure here says, oh, if I follow this, it's going to work. But guess what? It's not working. So how do you tell the client, this procedure you want me to do is absolutely stick it on the sweater because that's where it goes. Because what I'm actually doing is not going to, the same numbers are not going to be there. So the preheats, the post-heat, all that, how can you help us doing a procedure that actually, to me, when I do a procedure, has nothing to do with what's really going on in the field. The welder's going to follow my amps, it's going to follow my volts, it's going to follow my wire speed, it's going to follow with that's it, and that's it. But can you guarantee me the same numbers that I did when I did the 300 by 150 plate?
All right. Okay. So your question is, you qualify on a little plate and then you weld a big plate.
Yeah.
I say it is, you have seen that it's not necessarily the same,
It's
right?
not.
Okay, so we have done some experiments like those in the lab, and we find that problem too. I'll tell you two things. One is, in the different times at different places, you might have different welders, the environment might be a little bit different, but you imagine you control for that, right?
As much as you can.
As much as you can, right? I mean, if you cannot control, if you cannot control it, there's no point in thinking about it. If you cannot control it.
Correct.
But if you can control it, right? There's something that when we see, and it's something we're exploring in the lab now. These are like lines of temperature. So imagine the torch is in the little circle. Either this is welding slowly, this is welding fast,
Yeah.
right? And this is very, very hot, like melting. This is a little bit less. Maybe this is 800. This is 500. This is 3, right? And imagine your plate is too small, right? The heat is trapped. It's not coming out like this. So something we have found in some experiments we did. So when we weld on smaller plates, things cool down slower.
It's almost like the heat is there, and all of a sudden you're watching it, and it actually goes to the edge. And I swear it hits the edge and bounces back into it.
Well,
I swear. I mean, it's I don't know.
Funny.
You can sit there and watch it with your thermal gun. You're going, what the heck is going on here?
Well, that's what they call heat accumulation, and that's a problem.
You studied that, QMAS, right?
Yeah.
You wrote a paper in the Welding Journal on that.
Yeah, it was
Right.
about cooling rate and
Right.
something in between the thick plate and thin plate. But in reality, these are two solutions. One is a two-dimensional heat flow assumption. The other one is a three-dimensional. As if that your plate has infinite thickness, it's a three-dimensional heat flow. If it is thin, heat is dissipating two dimensions. So reality is in between. But heat accumulation happens, and that's always a problem that is not taken into consideration in the equations.
We're working on that. You know the funny thing? The way you account for that, the way you do the mathematics is called the method of reflections.
Yeah.
Really, you assume it bounces back the way you said. So I don't know if for the case of a 300 by the plate you mentioned, if that really is a problem or not, but that is something we find that we have all these beautiful formulas, and they are off consistently related to the plate size.
Yeah, because when you're looking at a procedure, you look at finding the procedure, you get the data sheet. You look at the data sheet, and the data sheet says in the 47 says, hey, you can't weld past -18. So if I actually did the procedure in the summertime and it was 21 outside, and that plate took a lot longer to cool down, the whole thing, now I'm doing it -15. Am I following the procedure still? I'm asking, am I following the procedure still?
The funny thing is the answer to yes or no about following the procedure is it gets into law, right? It's more law than engineering, right? It's what is written, right?
I'm asking you, I'm not asking you, I'm actually asking you as an engineer, am I following the procedure? Will I get the same,
Right.
my dot's in the middle, you said I got wiggle room. If I did it right, I should have enough wiggle room that if it was at 21, now it's -14 outside, and I'm welding it, I should have enough wiggle room in there that it should still work, right?
Right. Look, there are two things you can do. For example, and if you were to call me on the phone and ask me that, right, and I said, I'll sell you an expensive research project. You said, no. Yeah, I'll sell you my consulting. You say, no. Then I would say, okay, let's look into this formula here, right? And you see it says T500 and T800, that's 500 degrees, 800, minus T naught. That's the preheat temperature, right? So I would say, all right, if I know my material, right, where was it? I know my material, what cooling rate gives me what hardness. So I would say I want to be in this range, right? And then I would go to this formula and say, okay, what range of preheats gives me the time in there? That's what I would do.
Okay.
And that's a first cut. And the beauty of this is that if you did one experiment, you can do this type of analysis in relative terms. Because really using these numbers here is not going to give you, be too close. No, it's not going to be close enough for what you want. But if you have 1 point, so you can do relative things, like say it increases by 30% or decreases or what it is. So that's what I would do.
Okay. And I can send you the plate, you can look for me?
Well, are you taking the research project? But we can talk a lot more about this, and these slides are available to anybody who wants them. Yeah.
We do a lot of supervision of repair of equipment. So we deal not with manufacturing, but usually one-offs, and we're usually 100 miles into the bush, and you're looking at this first well, and we've got to do like a vertical, putting these two pieces together, thickness A, thickness B. And we usually show up and everything's done. And you're like, wow, so what did you do type of thing. And we deal with at least 400, 500 welders, and it's the same story for the last 5, 6, 10 years I've been doing this. Is there anything that's going to help, say, talk to, I'm not sure if Nate or whoever teaches the welding to the welders to say, okay, yeah, there is some numbers you should be reporting, and like the materials, your heat, in your settings, like most of them don't even know their journeyman number, let alone what they yeah, they just is there anything to help us out in that regard, where you kind of teach the welders, like at the school level, to say, okay, wait a second, if you're going to have something that is welded on, when you go to the rigs and you're talking to the rig engineer or the rig supervisor and say, okay, is this going to be just something that you want to hook on, or are you going to have this certified? Because we do NET inspections, and we're usually in charge of certifying the weld or the repair that's done, but we give them pretty much zero numbers on this stuff. So when the welders should be asking the rig people that, you know, is this for certification or not for certification, or at least when they submit that they've done their job, that they submit like a ticket showing what they've exactly done, what position, what rod, what material they purchased. Is that something, I know it's completely different from the topic,
No,
is that a direction that...
What numbers do you want then? Shoot that out first. Are you looking at temperatures, what kind of rods we use?
I do actually have a sheet that if I can catch them fast enough, but I got a sheet that I'll give to them, and they'll say, make sure you grind and polish the areas that are grind out your cracks 100%.
Yeah.
If it's a very critical area, then we have to MPI to make sure you're taking the cracks out.
Yeah.
But usually the minimum that we have is your rod diameter, your bolt diameter, travel speed.
And are they given that expectation before?
No, there's no.
Why do you give the welder the expectation before? And I got to tell you that at Supreme Steel, we found that the problem was the welder did not get that expectation. So I can't give him a
He's
crack.
got to control it though. He's just,
But we're not responsible for choosing the welder. Usually it's the company, like the drilling rigs, that pick the welders. And there's about 500 of them out there.
That's your root cause notice.
Yeah,
Your customer should be providing that.
You got to give that welder that expectation. Once they do, they'll do it for you. Awesome.
Yeah. It's been pretty good in that way, but usually we show up and we end up doing the half-hour, 1 hour talk with them, and then they find out for the next time. But it's, you know, for me, I've been talking to like the welding schools and saying, are you teaching your welders to do this? Like a root cause, go to the place where all these welders come through the school and say, you know, these numbers here are important. And the guy that's certified would like to know these numbers. They're taught the procedures in school. They're taught how to weld the plates, but they don't document anything. They just do the invoice. That's pretty much the only numbers they write down.
But that's the key in so many of these items here is you can engineer the procedure, you can identify the limits on the parameters, but then you it all gets simplified, put on a piece of paper and handed to a welder. The welder will go and he will look at it and say, that's the same thing I've done over and over again. And I've known that I've done this, I've been able to do this, and I've been able to do something a little bit different that gets it done faster or better or easier or whatever it might be. And I haven't had any effects up till now. So without the explanation and education of the person that's completing the activity, we can design and engineer and you know, to the nth degree how very close to the edge we want to come. But the problem is that then you can design to the edge, but you have a hell of a time constructing up to that edge and not going over. So you have to identify, then you have this huge level of conservatism you have to apply to say, well, where's the center of that target? Where's your wiggle room? And I think your question about developing a procedure in a certain temperature, then taking it to minus 15 or minus 18, yeah. I think right now within codes we have a huge level of conservatism that we apply into it, and as the design and engineering develops and we get X80 and X90 and X100 pipeline steels and different metallurgy, we're eroding away from that level of conservatism. And you know, it's not welding old carbon steel anymore. It's all microalloy, you know, processed steel that we're assuming is the same thing we welded last year, 10 years ago, or 20 years ago, and it's not. So you're right. We have to be very careful how the design and the engineering goes into it, because if I think I'm not an engineer, but as I understand engineers that they want to really get to some point where they can increase productivity and decrease costs, but the construction industry has to be able to keep up and meet that expectation. I've got a couple comments this morning or this evening about the design and engineering consultants saying, well, you have to do it this way. Well, but I can't construct it that way. Well, it's not my problem. I'm designing it this way. It's up to the constructor to build it. Well, then we need to change our design consultant, I guess.
This thing you say, I heard it quite a few times, and again, I think like Julian can say much. I think one of the things that justifies our existence as doing welding at the universities, what arguments, you know for experience that some of those requirements make no sense, right? When they, right, or
we haven't seen the effects yet. That's the thing.
Oh, okay, good point. So, who's gonna settle that, right? And I think that's something we can do, and not always through our beautiful research projects, but through education. If you're surrounded by people who speak the same language, if you think, a funny thing, welding is not really an engineering field in practice. But everything else in life is an engineering. Your car is engineering, your airplanes, your air conditioner, your iPod, right? Like, so again, the question is really 0-0. And if we do it right and more people talk the language, we're not being like scientists or anything, but just saying, yeah, cooling rate matters, or there's a range. I think we should do. Hopefully we'll do it so much and so deep that we'll be #1 in the world. That is the reason I came here. But even if we're not #1, moving.
Well, I ask one more question.
Yeah, sorry, I wanted to, I think you won't, I'm one of the largest advocates of the need for more welding engineers. I think that we have, what we're discussing here is a gap between engineering and the practical application in the field. And that's a gap that needs to get narrowed. And it's not gonna happen by taking welders and teaching Rosenthal's. And it's not gonna happen from taking engineers and making them weld for 6 months.
Yeah,
But,
no.
trust me, I can tell you, because I've been both ends of the spectrum. I think what we need to do is create more welding engineers, empower them, and communicate down. One of my arguments to the reason why these procedures need to be continue to be developed the way they are, the target in the dark, is every time that happens, we teach one more welder a little bit more about metallurgy, and he might teach another welder a little bit more about metallurgy. So, I mean, don't get me wrong, I'm not a cynic. I'm just, how do we practically apply this to benefit industry? Well said.
All right, well, I think at this point, we can call it an evening, and certainly for Patricio, he gave us a lot of things to think about. I mean, a lot of things that go above and beyond some of the practices that we've been doing, and and the value of the discussion that we had here. I mean, you can certainly see many things to consider for developing procedures. And certainly, Patricio, for behalf of all of on the group and the chapter, we'd just like to present you with just a little measure of our appreciation for your discussion tonight. And thank you very much, and certainly look forward to perhaps in the future another presentation for us. And actually, we'll go from there.
Let's call the people.
Yeah, I'll see what it like it. So that wraps up our presentation for tonight. You can certainly see from the brochures and things. You can look online. We've got other meetings coming up over the next couple months. So if you're able to come on back, sign up. We'd very much appreciate you being able to come back and be with us another time. All right, thank you then.
Thank you.